All right, so now we're going to observe vector fields by integrating streamlines. Okay, so we're going to define this Lorentz thing, which gives us, which parameterizes this vector field, okay? For this example. Then we're going to define P. And then here we specify the parameters of the Lorentz partial the Lorentz differential equation. And then we apply. So what is VF? VF is like a vector field, okay? So let's plot it. Stream plot VF, grid size 10 by 10. Oh, grid size equals, okay? So this is from the Lorentz differential equation. When you pick like certain parameters for the differential equation, then you get a vector field like this, okay? When in a certain range of, in like a when the range of values is like within this cube, okay? And in the text here, you can't really see. You can just see a two-dimensional depiction of it, but when you have the interactive session in Julia here in the computer, you can turn it around and get a view of it, you know what I mean? Using the mouse, you click around a little bit, and the keyboard controls are there as well if you want to use the keyboard to manipulate it. Well, that's just the Mackie software, you know, visualizing streamplot. Anyway, I'm getting carried away. But the point is that this is a numerical representation of a vector field, and any vector field that we numerically represent can be plotted here. And so one of the things, examples here is the ODE solver in the Adapode package. So this is built on Cartan as well, provides both the Runge-Kutta and multi-step methods with the optional adaptive time stepping. So let's do an example of that. So we'll define the function as like this, 10.0, right? 60.0, 8/3. And then we'll define x0 then we'll define the initial condition. Okay. So this produces like an initial condition object for the differential equation solver, okay? Once you have an initial condition object, then you can, you know, solve a differential equation, right? Then we just pick a solver, multi-step integrator, fourth order, 2 to the minus 15 step limitation. All right. So that solves the, gives a solution. And how does this work? Well, we're just visualizing it with the Mackie software, but if you just run ODE solve by itself, this produces a Cartan TensorField, okay? So all these things are TensorFields, Cartan TensorFields, okay? And the Grassmann package is used as the foundation, like all these vectors and stuff, they're Grassmann elements, okay? They're three-dimensional vectors in Grassmann algebra, okay? And then the whole solution of the differential equation is a tensor field in the Cartan package. And the adapode package has a differential equation solver, okay? As an example, like all right, so let's get moving. So let's recall this is just some more text information from previous things I've written before. We'll just recall that there's like the first grade sandwich product, reflection by the hyperplane. I talked about this proof. I thought this is a pretty cool proof because it uses the geometric product, and you can think of it splitting up the way you can do this calculation. So it's a really nice proof, and I've discussed it before elsewhere. So I'm not, and then we have a lot of other information to discuss today. So I'll keep it moving for now. But there's a lot of interesting things going on here. Then there's the Cartan-Diogenes theorem. For every isometry, there is a way to express it as a composite of at most k reflections. Hence, there exist vectors nabla j such that, like this, okay. So yeah, this is a classical theorem. Just reviewing it here using this operator notation, okay. So this is stuff I've discussed before, like note that the elements of the transformation of this group preserve the inner product relations. The even grade operators make up the rotational group. Each bivector isometry is a composition of two reflections, okay. So the exponential map and the Lie group parameter special cases. This is a common special case when you consider the differential equation with its solution with the exponential map, and you have this Lie group parameter that you can think of as being 2x. Then you have this hyperbolic cosine and hyperbolic sine, or the cosine and the sine in the 1 plus theta omega. These are some of the special cases for the exponential series. And yeah, so this is just more information about the convention of the sandwich product, which I've discussed before in the previous presentation. But the sandwich product must be written with the reversion on the left side, otherwise the rotation is clockwise and opposite of the phase parameter convention of the Euler formula. For example, here's an example that you can take a look at and verify for yourself, so that it's rotating in the wrong direction, opposite of Euler. Whereas in this convention, it's in the correct Euler convention. So the sandwich, so we can take this insight and apply it to the sandwich product and how its convention and the reversion on the left side should be standard. Okay. but many authors follow the opposite convention of clockwise instead. So this is just a remark for people who care about the details about these conventions and things like that. If you don't care about the great details, you can skip this, okay? But we're just gonna keep it moving. All right, so this is another example involving this Riemann sphere in projective geometric algebra. So let's define a set of points like this. Okay, let's pull up this formula. Where was this? This one, right? Okay. So these are just examples that I've had on my documentation page for a while, but they're now re-examined using the TensorField formalism of Cartan. So this just gives you the same plot as before, but now we treat the result as a tensor field like this, okay? Okay, tensor field. All right. So it's a Cartan tensor field, has an open topology. Okay, so we have all this topological FiberBundle tensor field stuff. Okay, and then we can just plot it. It's very nice, very nice. This is a new formalism that's I've introduced in how to handle all this information. Let's try another example. So that was another one of those examples that I had on my documentation page, right? So we can now get the results here as a tensor field and study it like that, right? Like let's look at the curvature of it. Or I don't know. May not be very interesting, yeah. Let's look at the speed at least. Yeah, so it goes very fast at some point. Very interesting. Okay. Yeah, this. Let's take a look at this one. Yeah, so it's just another one of those examples. Let's see about the speed of this one. Okay. Yeah. Alright. But these are using this exponential function, right? So this is a rather I guess complicated calculation in some sense. So uses exponentials and different kinds of operator compositions. All right, then let's look at the final example. So that was for the Riemann sphere projection, okay? Now let's do the conformal geometric algebra. It's taking a while for some reason. What's it stuck on? Some kind of error? Oh, right. It required, I forgot, you had to, apply, oh, I forgot to, put that in there. Okay. There you go. All right, so we went through those examples. Let's move on. All right. So, let's make a product space over 2 dimensions. All right. So we've got a domain now. And we can do something like this. Tensor. Apply it to the domain. So what this is doing is this is producing a tensor field. Okay. This is a tensor field. And then we just take the stream plot of it, okay? So, and we can modify the result of this by changing like this from pi to pi over 2, right? Oops. We need another parentheses somewhere, or what? I put one too many. Okay. There we go. So now that's the circular one. And we can change the angle now using that. Pi over 4, okay? And we can add a reflection to it. So those are just some of the standardized examples that I've discussed for a while, but you can deal with them in TensorField formalism now. So we have the same thing. But note that V here, this is the same line of code, but V is a different thing now. After we redefined the basis macro, V is now a different algebra, okay? Okay, so we've taken a look at some of these examples. Now let's take a look at three-dimensional examples. Okay, we need... So that produces TensorField. Oh, I forgot to close this here. All right. Something ain't right. Oh, did I misspell this? Oh. I put a times instead of a plus. Yeah, so I was a little bit confused because the output didn't look correct, and that's because I need a plus instead of a multiplication right there. All right, so there we go. Now we get the correct plot. So that's the plot right there. So this is the plot that's displayed in a lot of images related to Grassmann.jl. I like using this as kind of a representation of what's possible with Grassmann.jl. So this is that tensor field that gets produced from that calculation, right? So okay, so let's do VDOM 2. Oh no. There you go, there's this one. It's another interesting one, I think. All right, so let's get into this. So this is the multilinear n linear Lie bracket. Okay, so while back, I uploaded a paper where I proved that there's this multilinear Lie bracket recursion formula, and what the proof of that formula is, and what the how it expands into different into higher order Lie brackets. So yeah, so that's something I wrote about a while back. I made like a video discussing it as well on YouTube, and published a paper and so on, and with the proof of the theorem. So I'm just gonna I have the theorem here just for reference. So if Lie bracket recursion is an n bracket is a sum of n minus 1 brackets, okay? This recursion can be explicitly explained from the unary rule like that, and then this is the typical Lie bracket, and then this is the ternary Lie bracket, and this is the one with 4 arguments and 5 arguments, and it can keep going. The multilinear Lie bracket recursion properly generalizes the bilinear Lie bracket to the n-linear case, and is analogous to the Koszul complex of the Grassmann algebra, but is fundamentally different due to multilinear Lie bracket being non-associative, unlike the analogous exterior product. So not only was I discussing this in the paper and whatever, in the video I published and all that, and the proof and everything, I actually had this implemented in the programming languages as well. So let's do this example, f1 of x. Let's get the typing out of the way. All right. Chain of cosine of x of 1 times cosine x of 2. All right. So we've defined 3 functions here, f1, f2, and f3, and then we've expressed them as vector fields in some way, and now we're gonna apply the Lie bracket, okay? So Lie, so we have stream plot of VF1. Let's take a look at it. Stream plot of VF2. So we have the stream plot of these different things, right? So let's take the Lie bracket of VF1 and VF2. Okay, so that's what's depicted here. And when we switch between these two, it switches orientation. You see that? It's the same result, but the arrows point in the opposite direction. And not only that, but we can make a ternary Lie bracket. Okay? And it's not restricted to ternary. It can take another one as well, like, you know, like do it like that. But that one doesn't look as interesting, I think. This is a pretty interesting one. And I like this one too. So I made them I think they're worthy of being examples, aren't they? For a multilinear Lie bracket. And I don't believe the multilinear Lie bracket is like a new idea, right? So the TensorField, the Cartan TensorField implementation with the geometric algebra and everything is a new thing, and then the multilinear Lie bracket is like a new thing I proved with the multilinear Lie bracket recursion formula, and I don't think like all these kind of features have existed in other like programming languages, at least like scientific computing. Like if you go into MATLAB, like your standard MATLAB or your standard, Python or your standard whatever programming language you use, I don't believe it was standard that you would have like you'd be able to do these kind of Lie brackets and stuff, like multilinear, like higher order Lie brackets too as well. Just casually like this, you'd be able to do them. So you can do them with my software. And there's a lot more you can do with all these things, but we just keep going right now to get through various things. Let's see, the sphere was defined. So we're gonna recall to So this is just a little fun example with the stream plot. Stream plot on a sphere. So we had this vector field, right? VF2, and we can put it on the sphere. So I don't know. This is a function. So the reason why I made this an example is because this is not like a default function you can easily do with a plotting software. So there's like some extra calculus that has to be done in order to transform the coordinates into the tangent space, so that you can visualize a stream plot in the tangent space as an embedding in the three-dimensional space. And so Cartan.jl helps make that possible. So And it makes for nice looking plots. Like, it's just interesting to look at, right? So definitely worth checking out just for that reason, like to try out the functionality and different things like that. Oh, that's an interesting one. I like that one. Let's take another look at an example, a heat flow around the airfoil. So in the flow geometry package builds on Cartan. So there's another one of these packages I made. This is just for my personal interest to provide the NACA airfoil shapes. So let's generate another mesh. So this is like a feature I created that will create like a representation of a NACA airfoil, like NACA 6511, that produces this type with this American NACA 4 convention with the Clark Y coordinate, so on. And this helped that, like, you could do I believe, yeah, that'll give you the lines of the airfoil. But we've made a mesh now. So this is the mesh with the airfoil. And I think I've demonstrated this before in another YouTube video somewhere. And these calculations, I've been doing these for many years, but I'm demonstrating them in this example now to show some of the capabilities that you can have. So this is just specifying some boundary condition data using geometry information. The exact meaning of all this is not so important, to just oh. Oh no, this is the example they gave. Stream.gtf negative 0.3 dot dot 1.3 negative 0.2 dot dot 0.2. That was okay. There we go. So that's the command for the stream plot. All right, let's define the function for kappa of z. Okay, so we're just gonna recall that. Okay, and so now that was solving the transport diffusion. So that was the heat flow on the airfoil. So that was just to demonstrate some of the finite element calculations, kind of standard. It's just to give an example. So those are some of the, so that was the solve Poisson and solve transport diffusion example, just to show how it works. And most of the finite element methods using Grassmann and Cartan, they automatically generalize to higher dimensional manifolds with tetrahedra, for example. And the author has contributed to packages such as triangulate.jl and tetgen.jl. So let's try another one of these. Oops. Gotta spell it correctly. PS, that was the name of it, yeah. So now we have this sphere, and we're gonna use that to tetrahedralize a mesh around the sphere, actually. So tetrahedralize cube sphere. And it's gonna have holes specified in it. So I forgot to export cube sphere over here. I guess I'll export it at some time in the future. So the way to fix that right now is to add flow geometry dot cube sphere, but it will be exported in the future, I think. So I just have not actually exported it at this time yet. So, but for the sake of these examples and so on, I should be exporting it. Dang, man, something's slowing down my computer today with this video processing, yeah. So there you go. So that produces this three-dimensional flow example around the sphere. So that was just another one of these examples that we're going to cover. So Maxwell's equations rewritten. Cartan has Nettelig edge interpolation useful for solving the time harmonic wave equation. So we can form Maxwell's equations using the Faraday bivector dA with dDA equal to 0. And I've solved this as a finite element method, showing a picture here, like as an example. We don't have the example here in the paper for this particular one because it's more complicated. But I've discussed this before previously in another video in another paper. So dDA equals 0. And we have Gauss's law and Faraday's law. And we have star d star dA equals J for Gauss's law and Ampere's law. And so then the Maxwell's equation simplified to a single space-time wave equation. This is the same thing I've discussed previously. So I've included this again one more time because I think it's an important piece of information to consider.